Welcome to Module 3. Here we will discuss and review continuous random variables. Most of the concepts in this module are actually the same as in previous modules, except we adapt these concepts to continuous random variables and continuous sample space. So to start with discrete random variables, we mapped out the outcomes of an experiment onto a real number line, and only certain numbers have a probability assigned to them. So create a picture kind of probability mass function, because each value has some kind of mass attached to it. In the continuous case, we anticipate that our probability will be slightly different, and it'll actually have some distribution to it. So there's going to be some width to these lines. From our past introduction to continuous probability and discussing probability of a single outcome, you may recall that it's not really practical to discuss probability of a single outcome for continuous case because it will be 0. Therefore, we want to discuss a probability of an event which includes a range of values. So from discrete random variables, we recall that we use the cumulative distribution function to discuss a range of values. So if we wanted to know the probability that x takes a value between a and b, we just subtracted the cumulative distribution function evaluated at b minus cumulative distribution function evaluated at a. Now this concept of cumulative distribution can be translated to continuous random variables because we can take the area under the curve over some range. And this way we can calculate the total contribution to a probability over this range of values. From your past calculus experience, you should recall that taking a sum over very small contributions, very small spacing, becomes an integral. Therefore, we can imagine that in continuous probability, the cumulative distribution function will be some kind of integral of some function. We don't quite really understand what this function is, but we can reason that, well, it has to be some kind of integral. And without right now getting into specifics of what this function is, we can see, well, does the cumulative distribution function apply to probability theory? And how do the new axioms translate in the continuous random variable case? So original axioms can translate as follows. At negative infinity, our cumulative distribution is 0, and that makes sense because we have not included any values. As we go to positive infinity, it becomes 1, and it's because total probability has to be 1, and something in between, it takes some values. And in addition, the third axiom is just the probability of x taking on a range of values is just the difference between the two values of the cumulative distribution function. Now that we have a concept of cumulative distribution function for continuous random variable, we'll have to go back and find what is the equivalent for probability mass function for continuous random variables. What we really would like to do is to be able to compare two events. For example, if they occur over the same range, it would be nice for us to be able to somehow compare the relative probabilities. So here, if we have two events, we'd like to be able to compare which event is more likely to happen than the other. And intuitively, we know, well, we take the area of those and we could compare it. So what we're interested in is this probability as the range of our values that x takes becomes smaller and smaller and smaller and becomes infinitesimally small. And as we know, we can express this probability using delta, which is infinitesimally small interval. And we can rearrange the cumulative distribution function, and we can then take the limit as this delta goes to 0. So that means that the derivative of the cumulative distribution function gives us the probability per length. So it's essentially a density as compared to before we had a mass. Now this is a density. And what this density does, it describes a probability around this value x1, but not exactly at that value, because we know that probability of a single outcome is 0. So that's why probability density function describes the probability around that event, not at that event. So now we would like to use this definition of probability density function to define what is a continuous random variable. And we'll use the following definition that continuous random variable is continuous if it behaves like a continuous random variable, as we like to do in math. And that is to say that probability that x takes on some value b is going to be defined as the integral over a range of values of b of this magical function that we call probability density function. And we should caution that it should be reasonably well defined over this interval b in order to be integratable. And as we have to do it for other functions, we could reinterpret the axioms of probability in terms of probability density function and what they mean in that context. And as you can see, all this means is f of x has to be greater than 0. It has to integrate from negative infinity to 1. And cumulative distribution function has to be the integral from negative infinity to some value x. This is different in a way that we don't explicitly specify that probability density function has to be less than 1. Whereas before, we explicitly specified that probability mass function has to be less than 1. And that is because it does not necessarily have to be less than 1. Because as long as we can integrate it from negative infinity to infinity and get 1, it could be greater than 1. In fact, it could be very well much greater than 1. As long as the integral is 1 and it's never negative, it is fine and meets the axioms of probability. Now, let's look at an example of continuous random variable. And the most basic one is the uniform one that is uniformly distributed over some range. So it may present itself as this. And you can see that it's defined over 3 intervals, really. Before A, between A and B, and after B. And obviously, one of the first questions we might ask, what is C? Well, based on the previous axioms, this has to integrate to 1. Therefore, we know that C has to equal 1 over B minus A, because the total area has to be 1. And using this, we could create the cumulative distribution function. Notice we start with the cumulative distribution function because it's a lot clearer, because probability density function is a bit strange for us because it defines probability for events that should be 0. So what is the probability that x takes on a value that is less than A? Well, in that case, we notice that it will be 0. Between A and B, our cumulative distribution function will be the area, as defined here. And that area will be base times height for that rectangle. And the base will be x minus A, and the height will be C. And then as we get to values beyond B, well, by axiom of probability, this has to be 1. So now to find the probability density function, all we have to do is take the derivative of the cumulative distribution function, and that will be C on the range from A to B, and otherwise it will be 0. Next, we would like to examine what happens to our expected value in case of continuous random variable. And here we have an advantage of calculus for us, because now our summation becomes integration, and this becomes a lot easier to calculate than it was in discrete case. In addition, it's a lot easier to see a lot of the corollaries that we derived in discrete case. For example, if we have y, that is the derived random variable of x, we don't necessarily have to compute the cumulative distribution function of y as well as probability density function of y in order to find the expected value of y. We could just directly use probability density function of x. Next, we would like to look at the variance. So applying the direct equation here, we can see that we get this quadratic term in the integral. We could expand this quadratic out and split up this term into 3 integrals. And you can see that here, this is essentially expected value of x squared. This is a constant times x times cumulative distribution function of x integrated from negative infinity to infinity, which will be equal to expected value of x, as well as last part, which is once again a constant times the integral from negative infinity to infinity of the cumulative distribution function, which will equal 1. Putting all of this together, we derive the equation that we had before for discrete random variables, that variance is actually the expected value of x squared minus expected value of x squared. To derive affine transformations for continuous random variable, just as we did in discrete, as well as the affine transformation for the variance. Now let's go back to our example of a uniformly distributed random variable. What's going to be the expected value of x? Well, we could do it mathematically. Take the integral from a to b of x times our distribution function. And we could do this integration, or we could look at this function and say, well, this is symmetric. So intuitively, we know that the average value should be in the middle. And if we were to do the integral, we'll get the same result. In addition, we could look at the variance. And if we were to do this integral, we will get the following result, that our variance is b minus a squared divided by 12. And this is the uniform continuous random variable, which means that every outcome over some range is equally likely. So from now on, we don't need to really evaluate our expected value every time and variance. We can just use these set of equations and just apply them to the case that we have. Or if you want to, you could always apply the equations from the definitions. Now let's take a look at another example of a continuous random variable. In this case, it has this complicated form. So I might ask, okay, what is C? Once again, we'll define C by applying axioms of probability. That is to say that we need to integrate from negative infinity to infinity this function. And in fact, we're actually not integrating from negative infinity to infinity, but we're integrating from 0 to infinity, because otherwise our function is defined as 0. And if we do this integral, we'll get some value. And we set this equal to 1. As you can see, this requires doing integration by parts. So you should review that material and get comfortable with it. So next we might ask, okay, what is the probability that x takes some value from 0 to 4? Well, this will be just the integral from 0 to 4 of our function. So then if we ask, okay, what is the cumulative distribution function of this random variable? Well, in that case, recall, this is the integral from negative infinity to x. But in this case, for any value that is less than 0, our integral is going to be 0. So we can easily just change this to 0 to x. So then we might also ask a question, what is the probability that x takes the value from negative 2 to 2? Well, this is more or less straightforward integral from negative 2 to 2, except our function is defined as 0 on the interval from negative 2 to 0, so that integral becomes 0. And we just worry about the right integral. And this is why we make sure to always specify that 0 in our definition of a probability mass function and probability density function. Now let's talk about how do we derive a new random variable from existing ones. And as we've been talking about, for continuous random variables, it's a lot easier to think about cumulative distribution function and then get the probability density function. And that is the approach for all of these problems, really. So for example, if we ask what is a maximum of 3 uniform independent random variables? So we start out with know what random variables are. So the first thing we might ask, okay, what is the cumulative of that? So now how do we apply this to find the cumulative distribution function of the maximum? Well, if we write this out, what does this mean? By definition, this means that we're looking at the probability of this maximum being less than some value z. So what does it mean for a maximum of 3 numbers to be less than z? That means each one of those numbers has to be less than z. And because in the beginning we stated they're independent, we could actually split this up into 3 individual probabilities. So that's how we can come up with that our cumulative distribution function has this form, but of course we need to specify the limits. And so now to find the density function, all we have to do is take the derivative of it and assign proper limits to it. So the derivative of it is this. And once again, this is going to be defined from 0 to 5. And it's going to be 0 otherwise. So let's recap how we find the probability density function of a maximum. So first we approach it as a cumulative distribution. So we want to know what is the probability that the maximum of 3 numbers is going to be less than some value. Well, intuitively, you know that if the maximum is going to have to be less than some value, then each one of those numbers by themselves have to be less than that number. And if they're independent, that means you could break this up into product of 3 cumulative distribution functions. And this works great for a maximum. Now, how about a minimum? Well, you say, okay, if we're trying to find the probability density function of a minimum of 3 random variables, we could try to approach it the same way. Let's consider the cumulative. So in cumulative, we're going to ask, what is the probability that the minimum of 3 numbers is less than some value z? Well, this does not make a lot of logical sense because the minimum is already the minimum of the 3 numbers. So the probability that it's going to be less than some value is not really a realistic probability to consider. And this doesn't really lead us to anything useful.
So we kind of have to change the probability question and look at the complement. So if we look at the complement of this, the cumulative distribution function is a probability of 1 minus a probability that our random variable is greater than some value. So applying this to the minimum, we will have to find what is the probability that the minimum is going to be greater than some value z. Well, if the minimum is greater than some value z, that means x1 has to be greater than z, x2 has to be greater than z, and x3 has to be greater than z, right? Okay, so we can write it like this. And of course, if x1, x2 are independent, then we could break this up and say that the cumulative distribution of a minimum of 3 random variables is going to be 1 minus the probability that one of those random variables is greater than z, times the probability that the other one is greater than z, and the third one is greater than z. And then we could express this out as the cumulative by once again taking the complement. And we end up with an equation something like this. And then once we have this equation, we could find the cumulative distribution, and then we take the derivative to find the probability density function. And then from a probability density function, we could find what is the expected value and the variance.
The next random variable is exponential, and it has quite a unique place in probability and in real-world applications. And for our class, it has the following form of lambda times the exponent of negative lambda times x, as defined from 0 to infinity, and it's 0 otherwise. So if we take the integral of it and find the cumulative distribution, we get the following equation. And we can plot this, and it looks like this. So now to find the expected value of it, all we have to do is integrate lambda times x, e to the negative lambda x, dx from 0 to infinity. And if you apply the equation and find this integral with x squared, you'll have to do integration by parts twice. Go through the math, you'll find that the variance is 1 over lambda squared. This distribution is frequently used to describe the time until some event occurs. And that means the expected value will be the time. And it means lambda then becomes the average rate. So it becomes 1 over time, which is a useful description of an exponential, because if you notice from the form, the only thing you need to know about this distribution is lambda or 1 over lambda. So either the rate or the expected value. If you look at this cumulative distribution function and the probability density function, you might recognize something that we've seen before. And in fact, this is very similar to the geometric. In fact, they have similar shape and a same unique property that we'll look at next. So here we're an example of a light bulb, and it has some characteristic time until it burns out. That can be modeled as an exponential random variable with parameter lambda, and we've turned on the light bulb in a room and we've left. We come back sometime later, and the light bulb was on, so we would like to know, okay, how much longer will this light bulb operate? So once again, let's start with the cumulative distribution function, except in this case, let's actually look at the complement of the cumulative distribution function, because we're interested in what is the probability that our lifetime is greater than some value, because we know that at time x, it is still on. That means the expected value that we're looking for is for time greater than x. So now we can look at this problem. So we have the traditional lifetime of our bulb, and we looked at it at some time x, and it was still on. All right, so now we can construct our condition of probability, because we're wondering what's going to be our lifetime of our bulb, which is x plus t star, given that our lifetime of our bulb was initially greater than x. Well, using the condition of probability, we can write out the explicit equation, and we can see that this condition is redundant, because this is probability that our time is greater than x plus t star, intersection with time is greater than t star, which are the same conditions. And now we can plug this in and get the following equation. And then you can see that we can actually reduce this further and simplify out and just get e to the negative lambda t star, for t star being greater than 0. And notice that this looks exactly as the normal complement of a cumulative distribution function of a geometric random variable. Therefore, we expect that the expected value of this remaining portion will still be 1 over lambda. So that is to say, what happened in the past, once again, does not influence the future distribution of our random variable. And if you think back to the previous concept, right, this is because we have this distribution, but then we need to scale it to make it add up to 1. And when we scale it, it looks just like our original distribution. So this is a memberless property of exponential random variables. And it is similar to geometric random variables, where the past observation does not influence the future outcome. And in order to make sense of this problem in terms of lifetime, you could think of a lifetime of the light bulb in this case as the time that it takes for a light bulb to reach 50%
of its intensity.
Right? So when you buy a brand new light bulb, it could be outputting 500 lumens. So the lifetime would describe how long it would take it to get to 250 lumens. If you left it on and it's on, then you come back into it, it may have decayed down and now it's 300 lumens. So now its lifetime will be the time for it takes to get to 150 lumens. And that original lifetime and the new lifetime will be the same. And this is a fundamental property not just for probability, but also to other fields of study, because in nature, a lot of processes are exponential, chemical reactions, cooling, they're all exponential. And a lot of times we would like to know, okay, what is the cooling process? We would like to fit the equation. But the problem is we may have some cooling process, but we may not necessarily always be able to get down to time equals 0. So we will always miss some information about our process in the beginning because we're not able to observe it. For example, if we're putting a sample into a cooler, we might not be able to get its temperature as we put it in the cooler because it takes us some time to walk away. So we always are missing this initial information about our experiment. So it would seem like this would make it impossible for us to fit this rate and describe it. But because most rates are exponential, it doesn't matter if we fit our exponential here or here, we will still get the same rate constant.
There's a lot of similarity between a geometric random variable and an exponential random variable, including memberlessness and how we could possibly condition it on whether or not something occurred within a certain amount of time or it did not.
Another random variable we might encounter is a Gaussian, and it has this familiar shape that we might have seen. The reason it's important is because in nature and in engineering, a lot of processes end up looking like a Gaussian, end up having this distribution. For example, distribution of grades in our class, I would expect it to be close to a Gaussian. You know, with so few people, it might not be, but if we squint, we'll see it. In addition, if we combine many random variables, as we will see in future modules, we will get a Gaussian random variable. And that's an important property of it. So in this class,
we will utilize the following equation of a Gaussian. And we use this in order to normalize it and to make sure that we know what the mean is, as well as the standard deviation, just by looking at the equation.
An important property of a Gaussian is that an affine transformation of a Gaussian is a Gaussian. That is, if we shift the mean of a Gaussian by some number, or stretch it out, or change its variance, what we will get is still going to be a Gaussian.
So while the probability density function is well known for a Gaussian, the cumulative distribution function is a challenge, because that requires integrating from negative infinity to some value x of that form. And that form does not have a closed solution, therefore that value is often tabulated.
Because Gaussians are used so often. And notice because Gaussians are symmetrical, you don't need to evaluate this numerical integral from negative infinity to infinity. We only just need to look at it from 0 to infinity because we can find their side applying symmetry. And in engineering, we're quite often interested in this tail that happens here, that is essentially an exponential, and it drops off very quickly and becomes very small. But for a lot of engineering process and statistical process which occur with large number n, even though the probability is small because n is large, we do get a meaningful
contribution.
And that is why in your course materials you're provided with the complement of this cumulative distribution function, which provides this information about this small tail.
All of these tables are typically only provided for normal Gaussian.
That is to say, Gaussian is centered about 0 and has variance of 1. What about our derived Gaussian that is moved over or stretched out or squished? Well, this is an affine transformation, and we can write it as this.
And that means we can translate any stretched out and offset Gaussian into a normal Gaussian.
So that is to say, we can actually use the same standard table in order to find the cumulative distribution function of any Gaussian.
So let's take a look at an example of this. Let's say we have a Gaussian that is centered at 85 and has a standard deviation of 10. And we want to know what is the probability that that Gaussian takes a value less than 90.
Well, we could use the affine transformation to figure out how is this different from a standard Gaussian. So compared to a standard Gaussian, this one is moved over by 85 units, and it is stretched out by a factor of 10. So that means we could translate back that probability that y is less than 90 back to a standard Gaussian as probability that our standard Gaussian is less than 0.5. And for that, we can use a standard table to look up that answer, and then we know that that's going to be the same answer as the case of this Gaussian that is not standard. Now, we may have some experiments that have outcomes which involve multiple random variables, and it will be useful to describe both of them at the same time in order to be able to compare them to each other. To do this in continuous form, let's start with the definition of a joint continuous random variable from our handy function. So that is to say the probability that x and y fixed in values over some event A is the integral of x and y values over that event, given this function that we have yet to figure out. So if we think about x and y having some range, then we could figure out what the integral would look like. And if we take the limit of this range being infinitesimally small, then we'll come up with the following equation. And you should notice then that the probability density function becomes the probability per unit area. These are the values, and the distribution is this surface. And when we find the total probability of this event, we're actually finding the volume underneath this function. So probability density for a single random variable is probability per unit of that random variable. Probability density for two random variables is probability per area, and for three it is probability per volume. So probability density function is always probability per unit of our random variables. And similarly to discrete probability, in order to find just the marginal, well, all we have to do, because y partitions the space, we have to add up over all values of y, and in this case, that means we have to integrate over y, a joint distribution function, and we will get the marginal. To find the cumulative distribution function of a joint, all we have to do is integrate from negative infinity to x and from negative infinity to y, which is to say that our probability density function becomes the second derivative of the cumulative distribution function. We can also find the expected value of a joint distribution function similarly to how we did before, but now it's a double integration. And we can also show the properties of affine transformation still hold. And now to complete our joint probability density function discussion, we can talk about independence. So these two random variables are independent. In case the joint distribution function is just the product of their marginal. Now we started talking about conditional probability. Let's expand those definitions a bit more. So if we want to find the probability that x takes on some value, given that it's conditional probability of event A, we can write out this equation and take the integral in order to find the value. An interesting thing happens when we have random variable x conditioned on another random variable y. Right? Our standard definition says that x is conditioned to take some values, given that y takes a value. Now we know that probability to be equal to 0 because y cannot take an individual value. So in this case, we can get around that problem by saying that y is approximately some value y. So then this becomes approximately the conditional probability. And then we can expand this definition further and derive more useful forms of the marginal distribution function. And in addition, we can come up with a total probability or expectation equation. And these are concepts from previous modules where we talked about that if we want to find expected value of random variable x, then we may just find expected value of random variable x in various universes that could possibly exist, and then weigh them by the probability of those universes existing. And now that we have random variables, we know that y definitely partitions the space. So we can find the expected value of x in all the universes of y, and then just add them up based on the probability of all of those universes of y, and find the total expected value of x. Now let's look at an example of a joint probability density function. One of the most important things is to figure out what are your limits and plot this. So this is the region of our probability density function. So now if we want to find the marginal, all we have to do is integrate over x. To integrate over x, we need to consider the limits of our integration. And in this case, upper limit is 1, and lower limit will actually be y. And we can visualize this by just picking some values of y and see what the range of x is. And you'll quickly see that x goes from that line y equals x to 1. And because we're integrating over x, we cannot use x in the definition of the integral limit. What is the conditional probability of x given that y is 0.75? So notice now we know that x is going to be defined to be non-zero from 1 to 0.75. And normally we would say that this is 2. But notice if we integrate from negative infinity to infinity, this will not be 1. This will be 1/2. So we need to normalize it. So then this becomes 4. So now how do we find the conditional probability of x given y? Well, if you recall, we had the equation that it's the joint divided by the marginal. And we just found all of those. So this will be 2 divided by 1 minus y. 1 over 1 minus y. Once again, we define the limits for x and y, and then specify 0 otherwise. So frequently, we might want to have a derived random variable that depends on 2 other random variables. For this one, for example, we have y minus x is a random variable. So we'd like to find the cumulative distribution of z. In order to find this, let's first consider the limits of z. What are the possible values that z takes? Because y is from 0 to 1, and x is between y and 1. So it means that z is between negative 1 and 0. So for example, imagine where this sample space is, because it's a bit tricky to see. So for z is negative 1, that means y minus x is negative 1. And if we plot this, this is y x plus 1. Which is this line here. So this is z equals negative 1. We can do the same thing for z equals 0, and we'll see that this will be here. So we'll consider the cumulative distribution function, right? This is the integral from negative infinity to z. So what that would look like, to find the limits of integration, let's look at what the values of y are from here to here. So y then clearly goes from 0 to z plus x, and x goes from negative z to 1. We could also try to do this graphically, because what we need to find is find the area of the yellow triangle. Will be this side, which is actually 1 plus z, times 1 plus z divided by 2 times our probability density function of the joint, where 2 is our distribution function. For a simpler problem, let's look at the probability of throwing a dart at a dartboard some distance x away from the center. Once again, this is a bit hard to think about how do we do this in terms of probability density function. So we always start with cumulative distribution function. And for that, we're going to ask, okay, what is the probability that we hit the dartboard within some radius x? That is, we hit this within some area. Well, when we formulate the problem this way, the solution becomes a bit more clear, because we know the area of that region. It is pi x squared. We know the total probability of our event. It's pi r squared. So here we go. This is the cumulative distribution function, and it's just x squared over r squared over x between r and 0. And we need to add that for x less than 0, it is 0. For x greater than r, it will be 1. This is cumulative distribution function. So to find the probability density function, all we do is we take the derivative and define our limits. When we do that, we get the following answer. We can take this one step further and define some kind of payout or score that a player gets if they hit within specified radius t. In that case, they get a score of 1 over x. So to start, let's actually consider the range of values that we're interested in. So in this case, our x is how far from the center we hit, goes from 0 to t. and then it goes from T to R. So on the first interval, this is where we actually get some monetary compensation for us. And in that case, our compensation, interestingly enough, it actually goes from infinity to 1 over t, because of 1 over x. On the second interval, it actually is 0, because we don't get any monetary compensation for that. So now we can think about how do we create the cumulative distribution function of this monetary compensation. To do this, we can condition on the two cases that we have here for the range of where the dart hits and the implication on the monetary gain. So we're going to use the total expectation in order to break this event into two possible universes, depending on where we hit. So now looking at the first range of monetary compensation, the first term is just the cumulative distribution with t plugged in for x. The second term is the conditional, which we can break down using what the conditional is, and we can say that that's the intersection divided by the x less than t. And because we don't know what m is, we can plug in that m is 1 over x, and then we can get the intersection just in terms of one variable x. So then that intersection becomes that x goes between 1 over m and t, which we know how to find because that's just the difference of two cumulative distributions. So that whole expression goes to a single term. And the expression red becomes a probability that our monetary compensation is going to be less than something or equal to, given that we hit outside of our target region. Well, outside of our target region, our compensation is 0, which means the probability that we get some compensation less than or equal to 0 is always 1. So that's why that probability is 1. The other region of possible monetary compensation is between 0 and the smallest value we could possibly get, which is 1 over t. And that is the possibility that we hit outside of our target region, but in that region we still get 0. So that means that first term, the probability of that goes to 0, and the second term is still probability of 1 because of monetary compensation, even though we hit outside of our target region, is still 0. And we're looking on the interval from 0 to 1 over t. And now we can combine all that in order to find our cumulative distribution function and the probability density function of the monetary compensation.
For the next example, let's take a look at the following problem. We have a stick of length L, and we decide to break it at some random point. Let's call that point x1. So once we break it at some point x1, we decide, okay, we will take the right piece of it and then break that again. And we're going to break it again at some point x2. And we want to describe these 2 points, x1 and x2, with some kind of probability density function. So how can we approach this? First, let's look at the easy problem. How do we describe x1? Well, x1 is the first event, and it really does not depend on x2, and it is uniformly distributed between 0 and L, because x1 can be anywhere. So it's just a uniform distribution between 0 and L, and we know everything there's to know about that distribution. What about x2? Well, x2 is a little stretch because we don't really know what x2 is. But if we were to know what x1 is, for example, if we knew that the stick was broken at L over 2, right in the middle, then after that, we know that, well, that means x2 must have been broken somewhere between L over 2 to L. And it could have been broken anywhere along that length, and it would be uniformly distributed. So if x1 is fixed, then x2 becomes also a uniform distribution. And that uniform distribution goes from the fixed point x1 to L. So then that means we could write out the conditional probability density function of x2 as a uniform distribution if we know x1. And then, of course, in this case, x2 goes from x1 to L. Because remember, x2 defines the point where we break the right stick. Now that we have this, we can recall that the joint distribution is the conditional times the marginal. So now this joint distribution describes the whole event and tells us everything there's known about point x1 and point x2. And if we wanted to find out the marginal of x2, what we would have to do is integrate over all values of x1 of this joint distribution. So if we were to plot this joint distribution, it would look something like that, with x1 being represented by x and x2 being represented by y. And the marginal would be this integral. There's another question we might ask about this problem, and that is whether or not the three sticks we get form a triangle. Well, the three sticks we get are the following. So we get from 0 to L, our original stick. Then from 0 to x1 is a stick 1. And then from x1 to x2 is the second stick. And the third stick is from x2 to L. So if we were to express the length of all of those sticks, the first stick would be x1. The second stick would be x2 minus x1. And the third stick would be L minus x2. And for them to form a triangle, that means any two sticks added together must be greater than the third. Because if you think of a triangle, any two sides have to be greater than the third, otherwise they won't be long enough to form a triangle. So we could think of this as then there are some inequalities that we need to solve. So if we look at the first two sticks, so to find the probability that these three sticks form a triangle, we have the inequalities, and now we need to find what region satisfies all of those inequalities. So for our original experiment, we had that we took a stick and we broke it at x1 and then broke it at x2. So it means x1 could go from 0 to L. x2 also goes from 0 to L, but x2 must be greater than x1. It means that our original experiment is only over this sample space here. So now let's find where do these conditions intersect our sample space. So it means the region of interest in our event space that satisfies all these conditions is this one. So if we take our joint distribution and integrate it over this region, we will find the probability that these three sticks form the triangle. Often we may encounter a problem where we have to pick two random points along certain length. For example, let's say we have something that is 1 unit long, and we pick 2 points along that object. So points X and Y. And we can imagine that, well, X is going to be picked randomly and Y will be picked randomly. So really we can visualize the distribution as X will go from 0 to 1 and Y will go from 0 to 1. So our event space will be everything within this square. And everything's going to be equally likely because we said everything happens randomly. We cannot put any restrictions on it. But the challenging part with this is that if everything's equally likely, we never really know if X is greater than Y or Y is greater than X. So here we drew this as X is on the left of Y, but based on our diagram, that doesn't have to be true. There's going to be some cases where Y is going to be greater than X, and the case will be flipped. And in fact, this will happen 50% of the time, that Y will be greater than X. So it may be useful sometimes to limit our system to say, well, let's look at the problem where Y is greater than X, which means we could reduce the sample space first to half of what it was, and analyze it. And in this case, in this universe, everything is still equally likely. It's just we're using a subset of our universe. So this triangle still represents a uniform distribution of random variables x and y. It's just now we're dealing with the universe where y is going to be greater than x. And the reason we do this is that then we can actually have the correct order of zeros on the left, then x, then y, then 1. And then we could represent the length of sticks as x, y minus x, and 1 minus y. Because if we let the whole sample space be valid, that means we need to now account for different stick length. For example, if y is less than x, then our stick lengths are going to be y, x minus y, and 1 minus x, which is different in the first scenario and needs to be treated differently.
A problem that you may have encountered in reading the text is the problem of dropping a needle onto a grid that is spaced by d. And we can just very quickly go through it. So when you drop this needle onto a grid, it will be randomly oriented, and we can describe its position and orientation in terms of this angle theta that it forms, as well as the distance of the center of mass of the needle from the grid lines. So in defining the range of our values of x, we could say that x is defined from negative d over 2 to d over 2. But in fact, it doesn't really make a lot of difference whether or not our needle is below or above the line for our question, because our question is in regard to intersecting the line. So this way we can reduce this redundancy a bit and just say that x goes from 0 to d over 2. And since it is uniformly distributed, we know what the distribution will be. The second variable that we're interested in is theta. So we could say that theta is actually distributed from 0 to 2 pi. But because for this question, there's a lot of redundancy in how this needle is oriented. For example, it doesn't really make a lot of difference if it's oriented this way, right? Or if it's flipped over. So we can actually reduce the number of cases, unique cases, for us from 0 to theta pi over 2. So that is from 0 to 90 degrees. Because from 0 to 360 includes too many redundancies that we don't care about in case of this intersection. So since they're continuously distributed, we know what the distribution functions of these variables will be, and it will be this. So then we can combine it to find the joint distribution function. And we find these by simply taking the product of the marginals, because position and rotation in this case are independent. And now we can consider the condition for the needle to intersect one of these grid lines. And that condition would be that x is less than or equal to L over 2 sine theta. So in this case, to find this, all we do is we integrate over our region of interest, the joint distribution function, which is 4 pi over d. And we want to integrate with respect to x and then theta. So in this case, our x will go from 0 to L over 2 sine theta. And our theta, well, there's really no restriction on theta, so theta once again will go from 0 to pi over 2. So if we integrate this, we actually get the solution that probability of the needle intersecting the grid line is 2L over pi d. Interesting result of this is that now we have probability that actually defines for us what pi is. So if we can imagine doing this experiment many, many times to get a good value of p, then we can actually estimate a value for pi. Frequently, probably we come across problems which combine discrete and continuous random variables. So that's why we need to develop some mathematical language in order to be able to describe discrete random variables as pseudo-continuous. For this, we'd like to introduce impulse function as a function that is defined from epsilon over 2 to epsilon over 2 and has a height of 1 over epsilon. This way the area is always 1. And as we take the limit of this function as epsilon goes to 0, we get this delta function. The feature of this delta function is that if we integrate it from negative infinity to infinity, it will equal 1. And it really has only value at x equals 0. An interesting property of this impulse function is if we multiply by some other function and integrate it from negative infinity to infinity, then what happens is this function ends up having value only around where x equals x naught, which makes this delta function 0. This will take the value of that function, evaluate at x naught, and because the integral of our impulse function is 1, all we'll get back is that function evaluated at x naught. And this is known as the sampling property of the impulse function. Another property of our impulse function is if we find the cumulative distribution function of it, that is, we integrate from negative infinity to x, then before 0, it has value 0. It has some value around 0, and then afterwards it has value of 1. So in effect, it forms effectively a unit step when we integrate an impulse function. And in this class, we'll actually define that at x equals 0, it actually equals 1. Unit step of 0 equals 1. And you can see how this would be useful in order to reconcile discrete probability mass function and cumulative distribution to make it seem like a continuous using these functions. And now we can apply this concept in order to make a discrete uniform random variable appear as if it's continuous. And all we do is we translate that all the probabilities and assign them delta functions, and we get the following expression. And when we find the cumulative distribution function, we replace the impulse functions with unit steps. And this describes our discrete uniform random variable in terms of pseudo-continuous random variable. So these impulse functions and unit steps are useful when you have a discontinuity in your cumulative distribution function or your probability density function due to some implied conditions. We can look at one of these implied conditions in the following example. So let's say x represents the length of our phone call in minutes, and there's probability of 1/3 that the phone call is not made. So we will have duration of 0. Otherwise, the duration of the phone call is a random variable of 0 to 3 minutes. So we can consider representing this probability density function graphically. So from 0 to 3 minutes, we have a uniform distribution of the length of our phone call. Traditionally, this will be 1/3 because it's a uniformly distributed random variable. However, what is the probability of this occurring? So then this is actually 2/9, because right with the probability of 1/3, we do not make a phone call. So then what happens with the rest of that 1/3 probability? Well, that is going to be equal to 0 minutes of our phone call length. Therefore, we need to add an impulse function of height 1/3 in order to represent this additional probability that our phone call was not made, and therefore we count it as being 0 minutes. So then we could represent this distribution using delta function as well as the continuous part for y from 0 to 3 minutes. And of course, it will be 0 otherwise. Let's for a moment back up a little bit and look back at the total expectation value and how this was derived. On the right, I have a form of it from discrete time, where we had an event A that partitioned our sample space. So here we could partition our sample space using another random variable expression, the expected value of x conditioned on y. We can then rearrange the terms a little bit, and we can see that we have the product of the conditional times the marginal, which you know gives us the joint distribution function. And then if we rearrange it a little bit, we realize that when we integrate with respect to y, our joint, we get the marginal of x, and then we get back to the identity for the expected value. This becomes quite useful when we start talking about Bayes inference. We can use a similar approach in order to rewrite Bayes theorem to have a more useful form for continuous time. So original one had a conditional probability times the marginals, but we can actually rewrite this and get the denominator and the numerator to look very similar. And this allows us to calculate Bayes inference problems in continuous random variables. So let's look at an example of this using lifetime of a light bulb. But whereas before we had a fixed lifetime light bulb, here it's a random variable that is distributed from 1 to 1.5, and this is usually because of some fabrication process. And we would like to know, given that we've measured some lifetime, what could have been the lifetime of the light bulb as it was manufactured? So this is an example of Bayes inference, but notice we have two random variables and both of them continuous. So to solve this, we apply the previous equation, and we notice that this quantity. This will be 2, because this describes the distribution of our lambdas from 1 to 1.5. The next one is our lifetime of our bulb, given that we know the lambda for it, right? And this is the regular exponential distribution function that we had before, because this is conditional. And then the part on the bottom is the same thing, except now we integrate over all possible values of lambda. And in this case, our lambda goes from 1 to 1.5. We could do the same problem, but what if we consider that lambda is discrete? For example, if it's continuously distributed from 1 to 1.5, it only takes a value of 1 or 1.5. If we now write out the probability of our lambda, given that we observe some lifetime, we notice a slight problem with this equation. In fact, that this probability should be 0, because this is continuous, and continuous factor cannot take a single outcome. So therefore, this is going to be an approximation. And because we're going to approximate it for L, going from L to some infinitesimal space beyond L. And this is a bit of a challenge when we combine discrete and continuous random variables. But nevertheless, we can just use this approximation to continue deriving our Bayes inference. So if we keep going, we could derive the Bayes inference for this example as follows. So with this equation, we can combine discrete and continuous random variables in order to do Bayes inference of mixed random variables. So let's apply this case to a Gaussian communication problem. And this is where we have a signal that is -1 or 1. And it is being offset by some noise that is actually manifests itself as Gaussian with mean 0 and standard deviation of 1. So in this case, our two signals, being from -1 to 1, now are being received by our receiver as these two Gaussians. So now we might want to ask the question, okay, what is the probability that the signal we receive was 1 as a function of our signal strength, y? To do this, we just form the Bayes inference from the previous page. So let's see if we can find all these terms. This is the probability that our signal transmitted. It was 1. Well, this is simply p. Next part is going to be the signal that we receive, given the transmitted signal was 1. Well, this will be the Gaussian at 1 with standard deviation of 1. And the bottom part is the total signal that we could receive. So that would include with probability p, this is the normal Gaussian, as well as probability 1 minus p, it's going to be the Gaussian that represents the -1 signal. And if we plug our equations for Gaussian and everything, we can simplify those equations significantly and get the following expression. And if we plot the following expression, it has this form, and it describes the probability that our transmitted signal was 1, given that we received various signal strength.
Systems where we have two possible values that could occur are quite common in engineering systems. And that's why they're called bimodal systems. And this frequently occurs during classification. And because your correct value is not fixed, but it has some possible range of values that are acceptable, and your negative also is not a single value, it usually has some range of values, then you can imagine that these two ranges will overlap. And depending on your threshold, you might actually incorrectly interpret your results. So in this case, you could have a very wide distribution for positive values. And because of your threshold, some of it will be interpreted correctly, but some of it you will reject it. You will say this is a false negative because this is a positive, but because of your threshold, you've interpreted it as a negative. Similar situation happens with the negative. There's some negative that you will reject because it is below your threshold, but it is possible to get some negative value that is actually above your threshold, in which case you get a false positive. And these are frequently sources of error. So when we have this kind of system, we would like to characterize it and put some metrics on it, so then we don't need to describe everything. We could just give some parameters, and then everybody knows what we're talking about. So some of the parameters of interest for this are, and these are sensitivity, which is the true positive divided by the positive. So this is kind of the performance of your system, how well it can select positive values. And also specificity, which is the true negative divided by the total negative. Precision and accuracy. Those will characterize the system. And all of these values depend on a set threshold. So depending on how you set your threshold your accuracy, sensitivity, specificity, and precision will all change. So it becomes useful to kind of graphically analyze your threshold to pick the best value. And to do this, we use what are called the ROC curve or the false reject rate and the false accept rate curves. So ROC curve plots the true positive versus the false positive. And there you might look at what is acceptable rate of true positive versus false positive, and you will accept that threshold value. Or you might look at false reject rate versus false accept rate, in which case you're focusing completely on the error in your system. So in this case, you might look to the line that I mark here as equal error line. So this is where false reject rate and false accept rate are equal. And you might pick the threshold value that corresponds to that. There may be applications where your false reject rate and false accept rate are not equal. For example, in a highly secure system, you do not want to have any false positive. That is to say, you do not want to accept any negative value accidentally. But if you reduce that rate down to almost zero, that means you will have very frequently where what is positive gets denied access. So it gets rejected. And maybe this is okay, especially for high security. This means essentially when somebody comes up to the door, if they're an imposter, they'll definitely get rejected. But if somebody comes to the door and they're supposed to go through the door, well, once in a while they may get rejected. But they always have an opportunity to try again, and they maybe get in. So that would be a case of highly secure system. It could be a similar scenario in another case where it's low security system. So in low security system, you really don't want anybody to get turned away. And you don't really mind if you let somebody in who's not a member of the club, but as long as the members get in, you're happy. So that's an example. You would actually skew the threshold the other direction. Your low security application, but you might want to put your threshold here for high security.
Let's now formalize our error calculation in a bimodal system. So we have two sources of error. False positive, where signal from -1 gets interpreted incorrectly as positive because it is too high, and the false negative, so where our signal from +1 is too low and gets interpreted as -1. So we could find those by considering the Gaussian distribution tails. And then we need to weigh them. So if we know nothing about the system, then we will assume that -1 and 1 are sent with equal probability, and we will use that to weigh the two sources of error and then get our overall error in the system. So let's complete our view of Bayes' rule by finding out the rest of the combinations of continuous and discrete random variables to find our inference equations. Let's finish up now by taking a look at Bayes inference using the last form of the equation. So in this case, we have probability of getting heads, and that probability depends on the probability of our coin, which is described by this continuous random variable. It goes from 0 to 1. So if we wanted to know what is the probability of getting heads in a coin toss, well, normally this would be P, but in this case, this actually describes our P. So it doesn't have a constant probability. So we apply Bayes inference from previous page. So in this case, the probability of us getting a coin to land on heads is going to be probability that a coin landed heads, given that we know the probability that it is, times the distribution of all the probabilities of our coin. And the other part is just the probability density function for the random variable. And if you do the integration, you'll get a nice number. So next we might ask, given that the coin toss was heads, what was the conditional probability density function of the bias of our coin? We'll plug it in the Bayes inference. Notice that when we take the conditional probability of random variable with a random variable, we assume that the second random variable that is conditioned in the event becomes constant in this probability. And that's what allows us to actually solve this problem. So that's why this quantity becomes just B. It becomes similar to our coin toss. So in our conditional world, we'll say, okay, well, this B is no longer variable. It is a constant. It becomes like a probability of getting heads in a coin toss. So then probability of getting heads is just that probability, which is B. So we can plug in this equation and actually find then the Bayes inference of the bias of our coin, given that the coin came up heads. And then we can take this next step further and ask what is going to be the probability that The second coin toss will be heads. And this will give us a similar equation, and we can integrate it and find the answer that way.
In deriving continuous random variables, we have essentially established kind of a protocol of how we do it. Because intuitively, continuous random variables give us the probability density function, which isn't very easy to interpret without knowing everything about the process. So to derive continuous random variables, we have very much a step-by-step process to do this. So first, we will look at what is given, and we will find the probability density function or probability mass function for it, and the cumulative distribution for it. And then we'll look at the limits of what we know and translate them to the new limits for the random variable we are trying to find. Then we will look at solving the cumulative distribution function. For continuous random variables, we always go through the cumulative distribution function because the probability density function is not intuitive. So on solving that, we will formulate the question of what is the cumulative distribution function over an unknown variable, given what we already know. So in case we know x, we could substitute that in, rearrange our terms, and now we find the cumulative distribution of y in terms of x. So we can set up that equation, make sure that it goes from 0 to 1, make sure it's defined from negative infinity to infinity, and then we can take the derivative, and then we could find our probability density function. Once again, we'll do some sanity checks, make sure that it is defined from negative infinity to infinity, that it's not negative, and everything's set. And then we just do some math to find expected values and variances. And recall that there's a special case, the expected value of x squared. We very rarely need to compute that because if we know the variance and we know the mean, we know what expected value of x squared is. Another important skill for this part is to figure out how to plot the region of interest. So for example, we may have x and y that are distributed over positive values of x and y. So here we have x and y, and we know that x can take a value from 0 to infinity, and y can take a value from 0 to infinity, so it is defined on this range. And we might want to know what is the probability that y is going to be greater than 2x. So in order to find it, we need to find this region and then integrate it. So how do we find this? Well, the way we should do this is first let's plot y equals 2x. Right? This we can plot. So it would be this line here. All right. So now we need to find which side of it is y greater than 2x. Well, to decide which side of the line this is, we could try some points. So for example, here we have 0.10. Well, does that point satisfy our inequality that we have here? So is 0 greater than 2 times 1? No. That means this is not the region that we're interested in, and it means that this is the region that we are interested in. So this is the region y is greater than 2x. And that's how we would find this. Next example of problems we might want to know is a derived random variable z that is found by looking at x plus y, or maybe x minus y. So how do we do this? The important first step is to figure out what is the region of z and over which is it increasing, because we are going to have to find the cumulative distribution function. So we want to know where is it increasing. So in this case, let's say x and y are again distributed from 0 to infinity. So this is our x, this is our y, and in this region here, this is all of our probability. This is all the possible outcomes of our experiment. Now we want to know which direction is z. So let's imagine z equals 0. In this case, this is x plus y. So what does x plus y look like? X plus y equals 0. Well, this is going to be y equals negative x. And that will be this line here. So this, we then would label it, this is z equals 0. Okay, so now let's try z equals 1. So then this will equal x plus y. So then this is going to be y equals 1 minus x. So let's plot that. So now we can see that z is going to be increasing in this direction. So then when we think about doing the cumulative distribution function, then we should think about what is going to be the region in the case. So for z less than 0, then there's no area here that overlaps over our existing probability. So probability that z takes a value of less than 0 is 0. What happens if z is slightly larger than 0? Well, then it's going to exist over this interval here, and we will have to add up all of the probabilities in that range. For example, that is approximately line for z is 1/2. So probability that z is less than 1/2 is going to be the entire area that we have marked there. So once we find the cumulative distribution function, all we have to do is take the derivative to find the probability density function, and then we can find the expected value. As seen from this module, continuous random variables require a lot of math in order to find the expected value and variance and to handle derived random variables. What we could do is we could try to approximate continuous random variables as discrete in order for us to be able to easier solve them using common mathematical software. So let's assume, for example, we have the following distribution here of random variable x, and it goes from 0 to 2. And yes, this is relatively simple because we know the slope of that line will be 1/2, and that distribution is really 1/2 times x, and we could easily find the expected value algebraically. But let's see how we would handle this as a discrete random variable. So the first thing you do is you digitize this plot, right? And there's a video module that shows you how to digitize a plot.
And you'll probably get something like this.
And you can see we have a lot of points on downward slope around 2, and everything else looks somewhat okay. So the first thing you should notice is that this function is now heavily sampled at 2. So there's going to be a lot of probability that is centered at 2, which is not the reality in the situation. So the first thing you want to do is you want to sample this function at equal intervals. So here I'm choosing to make my x go from -1 to 4 in increments of 0.1. And then next I want to interpolate. So I will use the interp1 command, where I'm going to take the data that I digitized and I'm going to interpolate it based on my sampling array x. And that gives me my new data y. Now, if we compare what this looks like to what we just digitized, see the following. You see that now this is a much more representative function because it is equal spaced and it doesn't have all of the extra weight around 2. So one of the problems we might encounter is that some of those values in our new y array are going to be nan, because our algorithm could not interpolate over some range, and it would just return nan, and nan will be a problem because we may not be able to do mathematical operations. So one of the things we want to do is we want to now clean up this array to get rid of all of the nan values. So we will do this by cleaning up the x and the y to get rid of all the nan. So we could do this as xc equals x, but remove everything where y is nan. And we can do the same thing for y. All right, so now let's plot that and see what this new plot looks like. All right, so it's nothing different. It looks exactly the same as the before, but it is actually a smaller array because if you look at this, it's missing 2 data points that are nan. So now our new array xc and yc have no nan values, and we could do mathematical operations with them. Now I can find my expected value. Let's take the sum of xc, dot product with yc, and this will give us, this is our expected value operator. So if you run this, you find 15. You might be a little confused because how can our expected value be 15 when our random variable only goes from 0 to 2? Well, this is the first challenge of trying to translate a continuous random variable into discrete. And the problem is that our total probability is not 1 in this case. So because we're sampling our continuous distribution, remember, continuous distribution is probability density, is not probability mass. So what we should first do is we should normalize our distribution. So our new discrete distribution has the same shape, but then it has total probability of 1. So let's do that. So now let's create our new yc2, which is going to be yc
normalized by the total weight of yc. So now this array has the same shape and trend as our continuous random variable, but it is a proper probability mass function with a total probability of 1.
This is the distribution we can actually use to find expected values and variances. We could find what our expected value is, and this will be sum of xc dot product with yc2. And this is 1.36. And this is very close to what we would get if we did the integral using the slope equation. So if we did the integral using the slope equation, we would get 1 and 1/3, and this is relatively close. And then if we wanted to find the variance, we would do the same operation. We'd find xc squared times yc and minus this mean squared. So this shows you the steps we need to take in order to treat continuous random variables using discrete tools in MATLAB or Python. So first we have to digitize, then we have to equal distance sample it in order to get rid of a lot of redundant points that we have. Then we want to actually convert this from probability density function into probability mass function to make sure our total probability is 1. And then we can do all the traditional operations in order to find the expected value and variance.
And this completes module 3. So now you should be able to identify continuous random variables because they behave as continuous random variables, as well as calculate cumulative distribution function and probability density function for various random variables. And for continuous random variables, cumulative distribution function is the one we use to make sense of continuous random variables. And remember, it is the total probability up to some value. So it means it starts at 0 probability at -infinity and goes to 1 at infinity. In addition, we looked at the families of random variables as well as derived random variables and look at the expectation value and variance, as well as look at conditional random variables and dependence condition and Bayes inference in all 4 variants of it.